Okay, so welcome to section 7.2. In this section, we're going to talk about absolute value functions. In section 7.1, we talked about what the absolute value operation does, and we looked at how to evaluate some expressions with absolute values. So, in this section, we're going to talk about how to create a table of values, something we're familiar with, to graph an absolute value function. We're going to talk about how to sketch one, okay? And we're going to talk about how to identify the intercepts, the domain, the range, basically everything we did with the quadratic functions and radical functions, okay, when we graph them. So because an absolute value forces numbers to be positive, the absolute value function will do the same thing. Absolute value functions will always, take a look at this, always be positive, and it will include 0. So take a look at this graph. This is y equals absolute value x, the most basic, the base function, you could say, the base absolute value function. In blue here, okay, not my pen, but what I just circled, y equals absolute value x, this is the absolute value function. This is what it looks like. It looks like a y, okay, it looks a nice y. And that's because, let's for a second consider y equals x, the non-absolute value, so that's right here. That would be this entire line, right? Straight line right through the origin. Slope 1. Basically, there are two ways of graphing these, but all you're going to see is that the absolute value function of x is, of course, going to keep this guy the same because it's positive, but the moment you get to the 0, it's going to reflect. It's going to reflect to maintain a positive value for the function, which would be y, of course, right? And what this will come out to be is two pieces, okay? This is called a piecewise function, because you really do have two pieces separated by a very sharp corner, okay? And that corner is at the origin. So a piecewise function is a function that you can basically write out as two separate pieces. For instance, here we have y equals x if x is greater than 0, right? As long as x is over here, the graph looks like y equals x. The moment you go over here in the negative, that is x is less than 0, then the graph starts looking like y equals negative x. Now, the graph of negative x, okay, is simply going to be a reflection of y equals x. This guy is y equals negative x. And notice how you're basically honing in on this little segment, copying and pasting it over here. There's your two line segments. You have to learn this now, okay? So star this in your notes because it's going to be important later on. Okay, so we're going to do the first example. I go through the solution to the example and I graph it for you. We'll do a practice problem. Here we go. Consider the absolute value function y equals 3x plus 1. Determine the y-intercept and the x-intercept. So we'll do that up here, part A. To determine the y-intercept, for y-intercept, you're going to let x equal 0. Then you're left with y equals absolute value of 3 times 0 plus 1, which will come out to be y equals absolute value 1, which comes out to be 1. Okay? So you have an x-intercept at 1. You have a y-intercept at 1. Okay, the x-intercept will be let y equals 0. Now here's something that's important. We have 0 equals 3x plus 1. Because you're equating this to 0, okay, you can actually eliminate the absolute value signs, okay, because the absolute value of 0 is 0, okay? So let me just write this over here. So we can rewrite this as 3x plus 1. And this is because the absolute value of 0 comes out to be 0. And since this is an equal sign, okay, this will imply that we can drop the operation on 3x plus 1. This will allow us to do a very simple procedure, a little solving, and we get our x-intercept to be negative 1 over 3. Okay? Now, with those two pieces of information, we should be able to sketch the graph, which I will do it two ways. The first way, I'll show a table of values. Okay, table. This is the ever reliable table of values method, where you have x on one side and y, or f of x, on the opposite side. Okay. So, how you're going to do this, let me switch to black here. And let me just draw a line straight down the middle here. Okay, there we go. Excellent. Now, I'm going to just mark right off the gun here, right off the get-go, where our x-intercept is. It's at negative 1 over 3. Let's suppose that each tick here is 1. So that's 1, that's 2, that's negative 3, and so on. So that's 1, 2, 3. Okay? Then negative 1 over 3 will be roughly, and I'll do it in red, roughly right here. Hey, stop that. Sorry. There we go. And then your y-intercept is at 1. Like that. Come on. This program doesn't like when I do this. Perfect. Okay. Pretty big graph paper. I probably should have made this a bit longer out in terms of my spacing. That's okay. So from here, you actually can graph y equals 3x plus 1. Okay, the line y equals 3x plus 1. And what you could do here is you could actually do a reflection instead of using a table of values. Okay, like up here, what we did. You could graph this original line, okay, this guy right here, the whole thing, and then just reflect it to get the opposite one. And we'll do that later on. But for now, let's just suppose you wanted to use a table of values. Then what I would do is I would pick points on either side of the x-intercept. So I'd have negative 1 over 3 here. And that's going to come out to be 0. So let's pick points to the right and left of it. So let's just pick a point, let's say, let's do negative 2, negative 1, negative 2, and I'll go 1 and 2. Okay? So at 2 we get 6, we get 7. At 1 we get 4. Now this is the absolute value. So at negative 1 we have 3 times negative 1 plus 1. So we have negative 3 plus 1. So we have negative 2. So that's equal to 2. So this will come out to be 2. And at negative 2, you can do the math here. This will come out to be 5. Okay? So now you can just plot those points and just connect the dots. Okay, very reliable method. So when x is 1, while before 1, 2, 3, 4. When x is 2, I picked non-symmetric points, which was kind of annoying. Okay, let's omit this guy. Okay, that would be way up here. Okay, way up here. Let's just do negative 1 will be 2. And then, of course, negative 2 will be 5. Which, once again, it will be quite high up. Okay. It was foolish of me not to pick symmetric points. 1, 2, 3, 4, 5. We'll be right at the top. Right at the top. There you go. Okay, and our y-intercept's already in the middle, so when you connect the dots, what you're left with is that graph. Okay? So that's how you do it using excuse me, a table of values. Now if you wanted to state the domain and range, which we can do, and I'll do it in a different color, we can do over here. Domain and range. The domain here is basically x is going to be in elms of the real numbers, and the range will be y has to be greater than or equal to 0, where y is an element of the real numbers. Okay? That's because all y is positive, right? Everything's going up, and all the x's will be hit because these are going outwards like this. Then let's do part D, express as a piecewise function. This is where you're going to return to the definition, so I'll put that in. Go back to the definition of absolute values. Okay, the definition of absolute value states that y is equal to, okay, positive 3x plus 1, okay, if x, and in this case it's going to have to be greater than or equal to negative 1 over 3, or negative 3x plus 1 if x is less than negative 1 over 3, and that's this line right here going that way. Okay, so your point right here is basically I guess you could call it the vertex, right? You can call it the minimum or maximum, or sorry, it would be minimum of absolute value functions. Okay, that will be the point that will be symmetric. Okay, so let's do one more example. This time let's switch up the way we graph it, and this time we're going to do a quadratic equation. Now with the quadratic equation, you have to be careful. Obviously, the shape of the graph is going to look a bit odd. I'll show you a picture of what they look like. In this case, it looks like this. Oh, it was a poor decision to use a red. But this textbook in blue is the absolute value function. So it kind of looks like a hill, or it looks like a man sort of two arms above his head, you could say. Okay, there's his head. In blue is the absolute value function. Remember, the absolute value functions have to be positive. So basically, the moment the quadratic function dips below the axis, you just reflect that. See how it's reflected? You reflect it in the positive direction. And then you're done, and that's how I would suggest you graphing all of them, actually. Okay, table of values are convenient, but this might be a bit quicker and more efficient. So we're going to start off in the same manner. Okay, determine the x and y-intercepts. So we'll do the y-intercept first, which means we're going to let x equal to 0. So we're going to have f of 0, so y is going to equal 0 squared minus 0 minus 2. So we have y equals absolute value of negative 2, y equals 2. Then for the x-intercept, since it's a quadratic, you should expect 2 x-intercepts if it crosses the x-axis. If there's no solutions, that means it's shifted up. And if there's one solution, that means it's just touching the graph. Okay, recall these 3 different possibilities. Okay, so we're going to let y equal 0, which means we're going to have 0 equals absolute value of x squared minus x minus 2. Once again, since we're equaling it to 0, you can drop the absolute value sign, and then you can just factor it. This is 2 and 1, negative 1 plus, sorry, negative 2 plus 1, so x is equal to 2, x is equal to negative 1. Okay, those are your 2 intercepts. I now will draw very quickly on my graph paper. we'll switch to switch to red. So what I'm going to do is I'm going to graph this quadratic function without a table of values. But first, I'm going to need to know the vertex. There are a couple ways of doing this. If you memorize a way to find the coordinates for the vertex when you're in standard form, then you're good to go here. Then you're ready to go. Unfortunately, most of us don't have this memorized. Okay, but I'll give it to you right now anyways, just in case you forget. It's x equals negative, and I believe it is b over 2a. Yes. And from there, that's the reflection of symmetry, and you can go ahead and graph it. But let's suppose you forget this. Okay, then you're going to have to complete the square and to get into vertex form. So we have to move to vertex form, which is a quick procedure. So remember, to complete the square, you're going to have to first off bracket those first two terms. Then you're going to have to take half of this term right here, the coefficient. So you'll be left with x over x, and then you're going to square it. So it's x over 2, so you're going to get plus 1 over 4 minus 1 over 4 minus 2. Sorry, I'm writing so small here. That's x squared minus x plus 1 over 4. Then we have negative 1 over 4 minus 2, which is negative 9 over 4. So this is simply x minus 1 over 2, because this is a minus sign right there, squared, minus 9 over 4. Okay, that's what f of x is equal to, which means your vertex, okay, is at, the vertex is at 1 over 2 and negative 9 over 4. Okay, so you can plot that point, 1 over 2, and this time let's go up by 1, 2, 3, 4. 1, 2, 3, 4. Okay, 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, and 4. Okay, negative 9 over 4 is 2.25. Okay, so this will work out very well. So what we're going to be left with here is 1/2 and negative 0.25, which will be right here. Oh, you stupid thing. Switch to blue. Okay, that's where the vertex is. Then you're going to plot your intercepts. So one's at 2, the other one's at negative 1. 1, 2, 3, 4. Okay, so we have 1 here. I'll make these bigger. Here, here. Okay, you already can kind of graph this. The y-intercept is at 2. This is the y-intercept for the absolute value function, okay, which will be up here. However, for the original function, or not the original, for the non-absolute value function, okay, that is x squared. It always screws up here. That would be x squared minus x minus 2. If you're just to graph this function, okay, and I'll do it in blue, let's say. Actually, I'll do it in red because that's what they did up there. That's what we did before. Okay, this would be where the intercept would be, and what you would be left with is this graph. Supposed to hit all these points. Okay, this is the graph for f of x equals x squared minus x minus 2, but we're interested in the absolute value of this graph. So basically what's going to happen is wherever this graph is negative, okay, it will be reflected. It will be reflected. So that vertex will actually be right here. This is the y-intercept. So what you're actually going to be left with is that. And these will be positive as well. And there you go. In blue, you have the graph y equals, f of x. F of x equals x squared minus x minus 2. Okay, and so there you have it. That's basically how you would do these questions. The reason you don't really need to go through this vertex form per se, okay, is because if you knew, well, I mean, you're going to have to figure out this value for the y value for the vertex. So I suppose actually it is important to go through it. What this would give you is the reflection, the line of symmetry. Okay. So let's finish off this question. It says state the domain and range. Okay, so we'll do this over here. Part C, domain and range. So once again, domains are obviously always going to equal this. And the range will basically always be y is greater than or equal to 0. Okay, y is an element of the reals. Now the piecewise function in this case will be a bit tricky. Okay, the piecewise function, I'm actually going to erase part of my work right here. Okay, to make room for the piecewise function. For the piecewise function, what we have is the following. Y is equal, so this is part D. Okay, y is going to be equal to positive x squared minus x minus 2. This is the definition, right? If, now here's the key, when is equal to positive? When is it like this? Well, it's like this whenever x is less than negative 1, or when it's greater than 2 over here. So whenever y is, you could say less than negative 1, okay, or y is greater than 2. Then it's negative x squared. You need that bracket, remember, because it distributes in. If, and this is between negative 1. So if we have negative 1 is less than y is less than 2. Okay? That's how you express this as a piecewise function. So sorry for this long video. However, hopefully this makes sense going through and graphing it. I did leave myself a blank page to do some work, but I wanted to be able to reference the graph as we did this. So make sure you work on the practice problems. And once you feel comfortable, move forward to section 7.3.